In Chapter 3.3, we focus on risk identification tools within the define phase of DMADV. At this stage, the goal is to proactively identify potential risks that could prevent the new design from meeting customer requirements. These tools help teams anticipate failures, uncertainties, and constraints early before moving into detailed analysis and design. By systematically identifying risks related to process, technology, people, and compliance, we ensure that critical issues are addressed up front, reducing rework, cost, and design failures later in the DMADV journey. Chapter 3.3 covers key risk identification tools used in the define phase of DMADV to proactively identify and prevent design failures. FMEA for DFSS helps anticipate how a new design might fail and prioritizes risks before implementation. HAZUP systematically examines deviations from intended design conditions to uncover safety and operability risks, especially in complex or regulated processes. Fault tree analysis FTA works backward from a potential failure to identify root causes and logical failure paths. The POO matrix provides high-level screening by comparing multiple design concepts against criteria to eliminate high-risk or weak options early, ensuring only robust designs move forward into detailed analysis and design. DMADV is a design methodology, not a corrective approach like DMAIC, which means risks must be identified before the design is built rather than after failures occur. In this chapter, we use structured risk identification tools to predict what could go wrong in the future, understand why it might happen, assess the impact on customers and the process, and evaluate how likely each risk is to occur. By proactively eliminating or mitigating these risks during the define phase, we ensure the new design is robust, safe, reliable, and capable of meeting customer expectations, ultimately helping us build a truly risk-proof product or process. This slide illustrates how risk identification is practically applied in DMADV using tools like Design FMEA, where we systematically analyze what could go wrong in a new design before it is built. Each potential failure mode is evaluated for its cause, effect on the customer, severity, occurrence, and detection to calculate risk priority. By doing this early in the define phase, we can proactively eliminate or reduce high-risk areas through better design choices, controls, or error-proofing. This structured approach ensures the new process or product is robust, reliable, and aligned with customer expectations, reinforcing why risk identification is a critical foundation of successful DMADV implementation. Demonstrates the practical use of Design FMEA as a core risk identification tool in DMADV, where potential failure modes are identified early and systematically evaluated. The table shows how each function is analyzed for possible failures, their effects on the customer, underlying causes, and existing controls, allowing teams to assess risk before the design is finalized. By focusing on improving prevention and detection controls and defining clear recommended actions, DFMEA helps reduce high-risk areas proactively. This structured approach ensures that risks are addressed during the define phase, leading to a more robust, reliable, and customer-focused design rather than reacting to failures after implementation. This slide shows a process FMEA, which is used in DMADV to identify and assess risks within a process before the final design is implemented. Each process step is analyzed to understand potential failure modes, their effects on the customer, and the underlying causes, along with current prevention and detection controls. By evaluating severity, occurrence, and detection, teams can prioritize high-risk areas and define recommended actions early. Using Process FMEA in the define phase ensures that process weaknesses are addressed proactively, leading to a more stable, reliable, and customer-focused future state design rather than reacting to failures after launch. FMEA is a structured and systematic approach used to identify potential failure modes in a product or process, understand what can go wrong, analyze the impact of those failures on the customer, and determine their root causes. By evaluating risk and prioritizing the most critical failures, teams can decide which issues must be eliminated or reduced early. In DFSS and DMADV, the focus is on design FMEA DFMEA rather than process FMEA, because the objective is to prevent failures during the design stage itself, ensuring the final design is robust, reliable, and capable of meeting customer requirements. By using DFMEA in DMADV, teams can predict potential failures before the new design is finalized, allowing high-risk issues to be identified and prioritized early. This strengthens design specifications, reduces costly rework and redesign later in the project, and ensures the final solution is more reliable and safe. Ultimately, proactive risk identification leads to higher customer satisfaction by delivering a design that performs consistently and meets customer expectations from day one. In DFMEA, we start by clearly identifying the functions of the design, what the product or system is intended to do from the customer's point of view. For example, an ATM's function is to dispense the correct amount of cash. Once the function is defined, we identify failure modes, which describe how the design could fail to perform that function. In the ATM example, failure modes could include dispensing an incorrect amount, the card getting stuck, the screen freezing, or incorrect customer data being displayed. Identifying these failure modes early helps ensure risks are addressed before the design is finalized. In Step 3 of DFMEA, we identify the effects of failure, which describe what happens when a failure mode occurs and how it impacts the customer or the business, such as customer frustration, financial loss, safety risks, or damage to the organization's reputation. Step 4 focuses on identifying the causes of failure, explaining why the failure might occur in the first place, such as software bugs, sensor errors, incorrect calibration, power fluctuations, or incomplete requirements. Understanding both effects and causes is critical, as it allows teams to address risks at their source and design preventive controls into the solution. DFMEA risks are evaluated using 3 ratings: severity, which measures the impact of the failure on the customer; occurrence, which indicates the probability of the failure happening; and detection, which reflects how likely the failure will be detected before reaching the customer. In Step 5, each failure mode is rated for severity, occurrence, and detection, typically on a numerical scale where a higher number represents a worse condition, meaning greater customer impact, higher likelihood of occurrence, or poorer detectability. These ratings help quantify risk and support effective prioritization in the design phase. Step 6 of DFMEA, we calculate the risk priority number RPN by multiplying severity, occurrence, and detection. RPN equals S times O times D, where a higher RPN indicates a higher design risk that must be addressed first. In Step 7, we define recommended actions to eliminate or reduce these high-risk failure modes, such as improving requirement clarity, adding validation checks, strengthening control logic, enhancing material quality, or introducing automated testing. These actions are incorporated into the design to proactively reduce risk and ensure a more robust, reliable final solution. In Step 8 of DFMEA, the RPN is recalculated after implementing the recommended actions to confirm that design risks have been effectively reduced. DFMEA is not a one-time activity in DMADV. It is used iteratively across phases during measure to identify risks early, analyze to refine and prioritize design requirements, design to validate key design decisions, and before verify to ensure that residual risks are minimized. This continuous use of DFMEA helps ensure the final design is robust, reliable, and ready for successful verification. HAZOP, or Hazard and Operability Study, is a structured risk identification tool used to systematically identify potential hazards and operability issues in a process or design before implementation. It works by breaking the process into sections or nodes and applying guide words such as more, less, none, reverse, or other than to identify deviations from intended operation. For each deviation, the team evaluates possible causes, consequences, existing safeguards, and required actions. In DMADV, HAZOP is especially useful for complex, high-risk, or safety-critical systems as it helps identify safety, compliance, and operational risks early, ensuring the new design is safe, reliable, and fit for purpose before moving into final design and verification. HAZOP is a systematic risk identification tool traditionally used in industries such as chemicals, pharmaceuticals, manufacturing, engineering, and utilities or energy plants where safety and reliability are critical. In DFSS and DMADV, HAZOP is highly effective because it helps identify potential hazards and operability issues early in the design stage. Its primary purpose is to uncover safety risks, predict where design choices could lead to hazardous situations, ensure the process operates smoothly under normal and abnormal conditions, prevent catastrophic failures, and strengthen safety and regulatory compliance, making it a powerful tool for building safe and robust new designs. HAZOP is a systematic risk identification tool traditionally used in industries such as chemicals, pharmaceuticals, manufacturing, engineering, and utilities or energy plants where safety and reliability are critical. In DFSS and DMADV, HAZOP is highly effective because it helps identify potential hazards and operability issues early in the design stage. Its primary purpose is to uncover safety risks, predict where design choices could lead to hazardous situations, ensure the process operates smoothly under normal and abnormal conditions, prevent catastrophic failures, and strengthen safety and regulatory compliance, making it a powerful tool for building safe and robust new designs. HAZOP uses standard guide words to systematically identify deviations from the intended design or operation. Guide words like no or not indicate a complete absence of function, such as no flow in a pipe. More and less identify conditions where a parameter is higher or lower than expected, such as excess pressure or low temperature, as well as highlights unexpected additions like contamination, while part of points to missing components or incomplete mixing. Reverse identifies opposite behavior, such as reverse flow, and other than captures situations where a different substance or behavior occurs, like using the wrong chemical batch. Applying these guide words helps teams uncover hidden hazards and operability risks early in the design phase. HAZOP, or Hazard and Operability Study, is a structured method to identify deviations in processes, their causes and consequences, along with existing safeguards and required actions. In manufacturing, it helps detect issues like overheating, pressure buildup, improper mixing, or equipment malfunctions, preventing safety incidents and downtime. In services, it identifies risks such as system overloads, incorrect routing, data errors, and security hazards, ensuring processes remain reliable and secure. By analyzing each step and documenting causes, consequences, and safeguards, HAZOP allows organizations to proactively manage risks, implement corrective actions, and improve both safety and operational efficiency. Fault tree analysis, or FTA, is a structured, top-down approach used to identify the root causes of a system failure by visually mapping how individual faults or errors combine to create a major undesired event. In this example, the top event is an audit failure, which can result from audit object failure, audit process failure, or audit resource failure. Each of these branches is further broken down to show specific causes, such as unattainable or incorrect objectives, process errors, or resource issues like an unqualified auditor. The diagram uses OR, and gates to show whether a single fault or a combination of faults can trigger the higher-level failure, helping organizations systematically analyze risks, prioritize safeguards, and plan corrective actions before problems occur. Fault tree analysis is a top-down risk assessment tool that identifies the root causes of potential failures by starting from a defined undesirable event and working downward through logical gates to trace contributing faults. It visualizes complex interactions between components, human errors, and environmental factors, enabling prioritization of critical risks and supporting preventive actions. FTA is widely used in industries like aerospace, chemical, and manufacturing for design reviews, maintenance planning, and incident investigations, helping ensure both obvious and hidden failure pathways are systematically analyzed. Fault tree analysis, or FTA, is a structured, top-down method used to identify and analyze the potential causes of a specific undesired event within a system. It starts by defining a critical failure or top event and then traces backward through various contributing factors using logical relationships like and OR gates to map how combinations of component failures, human errors, or environmental conditions could lead to that event. FTA helps teams visualize complex cause and effect chains, uncover hidden vulnerabilities, and quantify risk probabilities where data is available, making it easier to prioritize preventive actions and strengthen system reliability. It is widely applied across industries such as aerospace, nuclear, chemical, and manufacturing, and is particularly valuable during design evaluations, maintenance planning, safety assessments, and incident investigations, ensuring that both apparent and subtle failure pathways are systematically examined. FTA is a top-down risk analysis method that begins with a defined top event, which represents an outcome that must be prevented, such as a machine breakdown, system crash, data breach, medication overdose, or a customer receiving the wrong product from this top event. The analysis works backward to systematically identify the underlying causes, sub-causes, and contributing factors, mapping how they interact through logical relationships using and OR gates. This structured approach allows teams to visualize complex chains of failure, uncover hidden vulnerabilities, prioritize risks, and implement preventive measures, making it an essential tool for safety, reliability, and quality management across industries like manufacturing, healthcare, IT, and chemical processing. DMADV fault tree analysis is used to understand complex failures and visualize how different system components interact, which helps in designing robust controls and uncovering hidden connections that might not be obvious. The process begins with defining a top event, such as ATM dispenses incorrect cash, and then traces backward using logical gates to map causes and contributing factors. A&D gates indicate situations where all conditions must occur for the failure to happen, while OR gates show that any one of several causes can trigger the failure. By laying out the failure logic clearly, FTA enables engineers and designers to anticipate potential problems, prioritize risks, and build more reliable and error-proof processes during the DMADV design phase. This example of fault tree analysis, the top event is a customer receiving an incorrect amount of cash from an ATM. Using OR gates, multiple independent causes such as a software bug, sensor malfunction, wrong calibration, or a currency jam are identified, any of which can trigger the failure. And gates illustrate situations where multiple conditions must occur together. For instance, a cash jam happening only if there is both poor maintenance and worn-out rollers. This approach helps engineers and designers visualize the failure logic, uncover deep-rooted design risks, and prioritize interventions to ensure more reliable and error-proof system performance, making it an effective tool for DMADV risk analysis. The POO Matrix is a high-level screening tool used to compare multiple design alternatives against a set of predefined criteria to identify the most promising option. It works by listing the options along one axis and the evaluation criteria along the other, then scoring each option relative to a baseline or reference, often using simple qualitative or numerical ratings. This structured comparison highlights the strengths and weaknesses of each alternative, makes trade-offs visible, and helps teams make objective, data-driven decisions rather than relying on intuition. In DMADV and design processes, the POO matrix is particularly valuable for quickly narrowing down choices, prioritizing features, and ensuring that the selected solution aligns with customer requirements and project goals. By listing the options on one axis and the evaluation criteria on the other, each alternative is scored relative to a baseline, making strengths, weaknesses, and trade-offs clearly visible. This structured approach supports objective, data-driven decision-making, reduces reliance on intuition, and ensures that the selected design best meets customer requirements and project goals. In DMADV, it is particularly useful for quickly narrowing down choices, prioritizing features, and guiding the team toward the most robust and effective solution. The POO matrix is a high-level screening tool used to evaluate and compare multiple design alternatives against a set of predefined criteria. It works by scoring each option relative to a baseline, which helps highlight strengths, weaknesses, and trade-offs in a clear, visual way. This method enables teams to make objective, data-driven decisions rather than relying on intuition, ensuring that the chosen design aligns with customer requirements and project goals. In DMADV, the POO matrix is especially valuable for quickly narrowing down options, prioritizing features, and selecting the most promising solution for further development. That helps teams compare multiple design alternatives against a set of predefined criteria in a structured way. By scoring each option relative to a baseline, it clearly reveals strengths, weaknesses, and trade-offs, making decision-making more objective and data-driven. This approach ensures that the selected design best meets customer needs and project goals, and in DMADV, it is particularly useful for quickly narrowing down choices, prioritizing features, and identifying the most promising solution for detailed development. DMADV, the POO matrix, is used to compare different design concepts objectively, reducing bias and ensuring that decisions align with customer requirements. It helps teams evaluate multiple options against critical criteria such as ease of use, accuracy, cost, reliability, implementation difficulty, safety, and impact on customer satisfaction, allowing them to narrow down choices early and avoid selecting suboptimal designs. The process begins by identifying the evaluation criteria, often derived from CTQs or requirements captured through QFD, and then scoring each concept relative to a baseline to visualize strengths, weaknesses, and trade-offs, guiding the team toward the most promising solution for further development. First, selecting a baseline design, known as the datum, against which all other alternatives are compared. Each alternative is then evaluated relative to this baseline using simple scoring symbols, plus if it is better than the baseline, 0 if it is the same, and if it is worse. After comparing all options, the results are summarized by counting the number of +0 and, for each design, which provides a clear visual of strengths and weaknesses. Finally, the best option is chosen based on these scores, and for greater accuracy, the criteria can be weighted to reflect their relative importance, ensuring that the selected design is both effective and aligned with customer requirements. This simple POO matrix example, the datum serves as the baseline for comparison, and to design alternatives, option A and option B are evaluated against it using the criteria of cost, reliability, speed, and ease of use. Each option is scored as plus if better than the baseline, 0 if the same, and if worse. Option B scores higher overall, showing advantages in cost and speed, while option A only improves reliability and ease of use. Based on this evaluation, option B would be selected for detailed design, illustrating how the POO matrix helps objectively compare alternatives, visualize trade-offs, and guide decision-making toward the most promising solution in DMADV. When put together, these risk identification and design tools provide a comprehensive approach to creating robust, reliable, and customer-focused designs. DFMEA helps predict potential failures and design features before they occur. HACCP identifies hazards and operability risks in processes. FDA uncovers deep-rooted causal failures, and the POO matrix guides the selection of the most promising design concept. Using them collectively ensures that the design is safe, customer risks are minimized, reliability is maximized, and costly redesigns are avoided, allowing only the best design alternatives to move forward in the DMADV process.